Right. So no, most of the material that I've been covering is from Relativistic Enlightenment, but for the other book that I have actually put, this Longaire's book, this is also shared in the material, is also very good, especially when it comes to synchrotron radiation and Compton processes. And this is actually, Compton processes are a huge topic and has a lot of applications. I'm only sort of scratching the surface of this very important topic. So I encourage you to read up this book as well. This is this high energy astrophysics book by Malcolm Longaire. Okay, so this is in addition to our Relativistic Enlightenment. Okay, so okay, let's get started. Okay. Okay, so today, till the last class, we had talked about the total synchrotron, total inverse Compton losses. Oops, what happened? Right, so we had this expression for inverse Compton power, which looked very, very similar to the expression that we had for synchrotron emission, right? So we had this, we derived this actually from these transformations from lab frame to the rest frame and back again. So the final formula was, this is just a recap actually. So the final formula was, right, so P, why is this so big? Why is the screen so big? Okay, I think this is better. Power inverse Compton was equal to, right, 4/3 sigma Tc gamma squared beta squared UPH, right? So this was the total inverse Compton power due to isotropic electrons with with gamma factor gamma, right? So so this was the expression. Beta, of course, is B by C. Sigma Tc, Thomson scattering cross section almost appears everywhere, wherever we are dealing with radiation, right? And so this was actually derived, and the point was that if you have electrons which have higher energy than photons, then electrons can lose energy and the photons can gain energy, and this process is called inverse Compton scattering, and the photon energy can actually be much larger than the photon energy of the scattered photons can be much larger than the seed photon energy, right, by a factor 4/3 gamma squared actually, right? So the mean mean energy gain, right, is like 4/3 gamma squared beta squared, and because the mean energy density is just UPH, sigma Tc, or the flux. Okay, and you recall P synchrotron power was identical expression 4/3 sigma Tc gamma squared beta squared UB. And last time I was actually telling you that CMB, particularly the cosmic microwave background, is a very important seed photon field, and that is equivalent to having a magnetic field of about 3 microgauss. Okay, so when you have a magnetic field which is equal to 3 microgauss, these two expressions for photons coming from the CMB is equal to this one. Anyway, now we'll actually move on to inverse Compton scattering spectrum, right? So, you know, we have actually followed the same program throughout all the different radiative processes that we covered, right? We did Bremsstrahlung, we obtained this spectrum which was flat and then exponential cutoff, and then we did this synchrotron emission, and we obtained spectrum for single electrons gyrating around magnetic fields with some pitch angle. Now we'll actually do the same for inverse Compton scattering, but I shall not derive the form of this expression, right? It's tedious, you know, and it actually involves a lot of working out, but for most of our purposes, we really don't need the derivation. What we need is we need to understand what it actually means. So that's what I'm actually going to focus on. It is actually motivated in the book, but it's somewhat tedious and I don't want to do it in class. Right. So let me write down the expression. Let me write down the expression. So the expression is J epsilon 1. So let me first write down and then explain what I mean, what the different variables here are. So n sigma t f naught divided by 4 gamma squared epsilon twice x log x plus 1 minus twice x squared. So this is the expression for this emissivity. So let me write down what these various variables are. N is the number density of relativistic electrons. So this is number per centimeter cube. So right, so this is capital N, and I have actually assumed that gamma is much bigger than 1 in this. Okay. Okay, what is F naught? F naught is number flux. So this is number of photons. This is not energy flux, this is number flux. So you have to multiply it by epsilon to get the energy flux. So number of photons per unit area, crossing per unit area, per unit time, per unit solid angle. Right. So this is actually equal to C times U epsilon omega by epsilon. So this is sort of like energy density. So this is energy density times C, which becomes flux. And in order to convert it into number, you divide by the energy of a photon, which is epsilon. Right, so this right, so this is U. So this is energy density of photons with energy epsilon with solid angle omega. So you know, this is how flux is related to the energy density. And then this J on the left hand side is the again number which I sort of recall I'm calling as this hash, number of photons emitted. So again, this is number, not energy, emitted per unit volume, per unit solid angle, per unit energy. And of course, sigma t is the Thomson scattering cross section that we all know. So and x is equal to epsilon 1 by 4 gamma squared epsilon. Right? What is epsilon? Epsilon is energy of photons, seed photons, before scattering. Oops. And this is after scattering, and this gamma is of course for electrons, relativistic electrons. What is their gamma factor? We are assuming a single, so the setup is something like this. So you have electrons with, they are randomly distributed, but their gammas, their random gamma is the same. So monoenergetic electrons, and you have photons which are also isotropic, going in all directions, right, in the lab frame, and their energy is also the same. So monoenergetic photons, and their energy is epsilon before scattering. So if one of these, so and we are assuming that this is much less than photon energy is much less than, in fact, this. We are assuming this, right? Can someone tell me why we are assuming this? I'm assuming that gamma epsilon is much less than mc squared. Throughout our sort of discussion, we have assumed this. This is what? Gamma epsilon is roughly epsilon prime, right? So epsilon prime is the energy of the photons in the electron rest frame, okay? And this we sort of obtain from the Doppler formula by putting theta is equal to pi by 2, so that cos theta, assuming isotropic electron distribution, just gives you 0. So basically this is the mean energy of photons in the electron rest frame, and we are assuming this so that we are in the Thomson limit. And so there is not loss of energy in the electron rest frame. So this means that this is equal to, the energy after scattering is the same as energy before scattering in the electron rest frame. Okay, so right, so this is the setup. So you have these electrons, you have these photons, and so one thing is whether these electrons will collide with these photons depends on this tau, right, which is just the n sigma dl, optical depth, right? But once this collision happens, once the scattering happens, this is the emergent spectrum of the scattered photons. So spectrum of scattered photons in the lab frame. Okay. Any question? So I'm not deriving this, I'm just stating this. So this is number density, area, flux, which is number of photons per unit area, per unit time, per unit solid angle. So number per unit volume, and this is energy. So this becomes right. So this becomes number per unit volume, per unit solid angle, per unit energy, and X is dimensionless. I can recall that these are number fluxes, not energy fluxes. Okay, so this is to be consistent with the notation of Rybicki and Lightman. Okay. So So this is like a single photon. This is monoenergetic electrons and monoenergetic photons. They have random directions, but they have the same gamma and same epsilon. Okay, and how does this look like as a function of x, right? So we can actually plot like j, in fact this is j. We can actually plot just a sec. So the energy, in terms of energy, this will be epsilon 1 j epsilon, right? Now this is number, this is the energy per unit area per unit time, or sorry, energy of photons emitted per unit volume per unit solid angle per unit energy, right? So that is what that is. So if we multiply it by epsilon 1, right? So this is proportional to, so that's epsilon 1 by 4 gamma square epsilon, which is x times twice x log x plus x plus 1 minus 2x squared. This is versus x, let's say, which is equal to epsilon 1 by 4 gamma squared epsilon. Right. Right. So basically, in the limit that x goes to 0, this is just proportional to x. So in the limit when x goes to 0, this goes to 0, this goes to 0, this is 1, and there is a x outside the bracket. So it sort of looks like this, log-log plot again. Whenever we have power laws, I prefer log-log plot. So it's proportional to x. Then it becomes shallower, and then when x exceeds unity, right? When x exceeds unity, this becomes right. This dominates, right? For x greater than 1, this dominates everything else. So it becomes negative, and there's an exponential cutoff. So this happens at 1. This is also consistent with the fact that epsilon prime is equal to gamma epsilon just a sec, gamma epsilon times 1 minus cos theta, right? And epsilon 1 prime is equal to epsilon prime. This is the Thomson. There's no P in Thomson. Thomson limit in which there is no exchange of energy. It's elastic scattering in the electron rest frame. And then epsilon 1 is equal to, again, gamma epsilon 1 prime 1 plus beta cos theta prime, right? So I mentioned that epsilon 1 max, for maximum possible energy of the scattered photon, is equal to, when this becomes 1 plus 1, which is 2 gamma epsilon, and this is again 1 plus 1, which is 2 gamma. So it is 4 gamma squared epsilon, right? So this is where you have this exponential cutoff. You can't have photons with energy larger than this, right? And then this is proportional to x here, and so this is a one mono energetic electrons and photons, right? So this is, recall, for synchrotron emission we did almost the same thing. We assumed a pitch angle alpha, we assumed some electrons with gamma, and we assumed magnetic field lines, and we obtained this fx, if you recall, where x was this factor omega by omega c, right, which is proportional to nu by EB by mc, and then there was this gamma squared factor. It's almost the same thing here. Here x is epsilon 1 divided by 4 gamma squared epsilon, which is nothing but like nu by 4 gamma squared, because epsilon is just h nu. Epsilon 1 is h nu, which is nu 1. Let's call it 1 times nu. So it's almost the nu naught is the photons, is the frequency of photons before scattering. So you see almost identical looking formula we have, right? There's a nu by nu naught, and there's a 1 by gamma squared factor in both cases. So in both cases, what happens is, so if you have, in case of synchrotron, you have an electron gyrating at this frequency EB by gamma mc, which is omega b, and so the electron is gyrating with this frequency around a magnetic field. It creates a photon which is at a frequency gamma cube omega b, right? Because of this light chasing light effect, all that we did. Then so this is synchrotron situation. In inverse Compton, you have seed photons of energy nu naught, isotropic, going in all directions, and there are relativistic electrons with gamma, right? So if they interact, you get a photon of energy, of order gamma squared nu naught. So it's almost like and this is like gamma squared EB by MC, and this is proportionality actually. But you see the same thing, that you get a boost of photon energy by gamma square. Here you get a boost over the synchrotron frequency or the cyclotron frequency by gamma square. Okay, and if you recall the form of this fx, the emissivity function was, it was actually shallower, and then again sort of a cutoff like this, and this was like x to the 1/3 in case of synchrotron, and then the cutoff happened at nu c, at omega c. So it had a similar nature. Okay, so there is a very, very close analogy between inverse Compton scattering and synchrotron emission. So you have to keep that in mind. Okay, any question? Please ask questions. Otherwise, it feels as if there is no one in the class. Oops. Okay, so let me what did I want to show? So I have actually put some material in this section, in the file section on general, and that material is actually related to right. So what is the material? One is this there was a JAP student last year who did a project with me, and he tried to do Compton scattering with a Monte Carlo code. Basically what you do is you simulate the process of Compton scattering, and you go from lab frame to the electron rest frame, apply the Klein-Nishina correction, apply all the once we are in that frame, we know the exact formula for scattering. So you have this, you just apply this whole program of calculating inverse Compton scattering. So this is actually quite useful if someone is interested in knowing a little more about it. And I mean, he has actually shown what exactly is done, and he's also shared the code, and you actually see that the photon spectrum indeed gets modified if the optical depth is high. And he's done various limits. Okay, so this is one thing. The other thing that I have put there is this classic paper by Thomson and Gould. Sorry, not Thomson and Gould, but Blumenthal and Gould. Right. So this is this paper which deals with Bremsstrahlung, synchrotron, and Compton scattering. So it sort of covers pretty much the things that we have been doing. And so, for example, this procedure of how we get the inverse Compton power is actually outlined here nicely, and he talks about this aberration and all that. And then he outlines how one gets this emergent spectrum of photons. Anyway, so the other thing is the book. This book. This is the book by Longaire, and here you can actually see this. Yeah, this is exactly what I just drew. Right. So this is slope 1. This is I nu versus nu by gamma squared nu naught. Here it's cutting off at 4, but I was actually normalizing it to nu by 4 gamma squared nu naught. So it has this characteristic shape. In fact, he also cites that paper that I just flashed. So do read, if you're interested in more details, do read all this material. This is quite important material, quite important process. Okay, so let me go back. I took this break because no one said anything, so I thought maybe I should say something which is lighter and tells you about what more resources you can look at. Okay, so now let me get back to where I was. Okay, so this is a single electron gamma spectrum. Now, what if you have a distribution of electrons, right? So, for example, if we have power law distribution of electrons, right? And again, we did it previously. So n gamma is equal to, say, constant times gamma to the minus p for some range gamma min to gamma max of the. Now we have a range of electron gammas. Here, this was done for a single gamma, right? That's why it's a function of gamma and 0 otherwise. So we have a distribution of electron gammas, which is a power law. Now, what happens in this case? How do you get the emissivity in this case? We have dE. So this is, let me just write down first. So this is nothing but energy per unit volume, per unit time, per unit photon energy. So this is sort of like nu, right? This is sort of like your nu. If you recall our specific intensity, this is sort of like your nu. H nu is epsilon 1. H nu 1 is epsilon 1. So how much energy comes in photons at this particular energy is what this specifies. So this is equal to, let me just write down and then explain, n gamma d gamma epsilon 1 j epsilon 1. So this j is just this one, and b epsilon v epsilon c by epsilon, and this is sort of like a flux. This is sort of like your f naught. So this is flux, number flux actually, right? So v epsilon times c is energy flux, and you divide by the energy of the photon, then you get the number flux of seed photons. So this is of seed photons. These right? So that's why we have epsilon, not epsilon 1. These are unscattered photons that we are talking about. Epsilon 1 is after scattering. Okay. Okay, so this is what we have. Now we know the expression for J epsilon 1, which is given here. So let me write this down. Let me just call this as function f(x). Right, this is just a function of x. Okay. Now, how do we integrate this? Now, you see the situation, we have a double integral. We have an integral over the possible gammas of electrons and integral over all possible seed photon energies. Right. So in the previous calculation, this was fixed and epsilon was fixed. Now we are integrating over all the possible gammas and all the possible seed photon energies. So what do we have? Let's see. So this is equal to this is this normalization constant. This is equal to 3/4 sigma Tc. This capital C, the normalization constant, integral d epsilon 1 by epsilon. This is just this, right? This ratio times v epsilon times integral from gamma 1 to gamma 2, right? So, or this is gamma 1, gamma 2, gamma min, gamma max, times d gamma. And if you look at this expression, this is just a tick mark. This is just a tick mark. Now we have, right, so n gamma is nothing but c gamma to the minus p, gamma to the minus p, and there is a 1 by gamma squared. So we have gamma to the minus p minus 2, right? Minus p comes from here and minus 2 comes from this one. Okay, and you have f of x, and x was nothing but epsilon 1 divided by 4 gamma squared epsilon, right? So what we have done is just substituted in that expression. So we have this, and this goes from gamma 1 to gamma 2. Again, we have a change of variables. I mean, very similar procedure as we did in synchrotron, right? Recall, we added up a lot of these. We had a power law distribution of electrons, and we added up synchrotron emission due to all of those and obtained like luminosity, or spectrum as a function of frequency, and that we are doing the same thing. And there also we did this change of variable. So x is equal to epsilon 1 by 4 gamma squared epsilon, and so gamma is equal to epsilon 1 by 4 epsilon times gamma, times x to the minus 1/2. So d gamma is equal to minus epsilon 1 by 4 epsilon half x to the minus 3/2 dx. So we just do this change of variable. What do we get? So this becomes 3/4 sigma Tc, capital C, epsilon 1 to the power of minus p minus 1 by 2 integral d epsilon, epsilon to the p minus 1 by 2 v epsilon integral x1 to x2, right? So gamma 1 and gamma 2 correspond to x1 and x2. X to the p minus 1 by 2 fx dx. This is what we have. So this is fx, and gamma can be written as a function of x and epsilon 1 by epsilon. And again, d gamma can also be written like that. And this is what we get. So this epsilon 1 to the power of minus p minus 1 by 2 is outside. And we have this expression. So you can actually see this x1 and x2. What is x1 and x2? So x1 is equal to epsilon 1 by 4 gamma squared epsilon, right? Gamma 1, and x2 is gamma 2. So there is a 1-to-1 correspondence between x1 and x2. But so this is something that in general depends on epsilon. In general, right? Because there is 1 by epsilon here in the limits. But if this integrand is peaked, right? If this integrand integrand peaks at x, which is far away from x1 and x2, if integral dominated by x less than x2 and much greater than x1, right? Basically, the integral does not depend on the limits. Then this is not a function of epsilon, right? In that case, we can take x1 to 0 and x2 to infinity, right? Because the integral is actually dominated by intermediate x's. In that case, this is independent of epsilon, and then this just can become, this will give you a number which can come out. So in that case, what do we have? We have, so in this case, we have dE.
So what are the bounds of E energy? You have not written, means.
Oh, no, this epsilon.
Yes, epsilon.
Epsilon goes from 0 to infinity, of course. I mean, all possible seed photon energies.
So, but it must be restricted, because of the rest mass energy of the electron.
Right, that's correct. So, what I'm assuming is that this will still be dominated by, this integral will still be dominated by guys which have mc squared by gamma. Right. So basically, this integral also will not be dominated by the upper and lower limits. Okay. Okay. So this is all standard tedious algebra, but the point is the dependence. Right. So this is actually proportional to. So this will just be a number. This will just be an integral over the given seed photon field energy density. So this is for example, CMB and whatnot. So, but the point is, this is proportional to epsilon 1 to the minus p minus 1 by 2. If you recall, our synchrotron, the synchrotron spectrum was proportional to nu to the minus p minus 1 by 2. Almost the same dependence, right, on the power law distribution of the electrons. Okay, and there is a physical reason for that as well, which I'm going to highlight. So, for example, for the CMB, there are these standard integrals which are given in the book. Okay, so I'm actually not going to write the tedious formulae in detail. If these are needed, You can refer to the book, but the procedure is important to understand what we are doing. Previously, we assumed one epsilon and one gamma, and now we are integrating over all possible gammas and all possible epsilons of seed photons. Okay, so you can go back here in this formula. This formula depended on gamma and on epsilon. Now we are integrating over all gammas and all epsilons. So the final formula should not depend on gamma and epsilon, and it actually does not, because these have been integrated over. Now let me show you why we get the same dependence in synchrotron and in inverse Compton. Right, so the idea is actually simple. Let me actually schematically draw whatever J nu as a function of nu, right? We know for a single photon, the synchrotron sort of looks like, this, power law and a cutoff, a power law and a cutoff, and a power law and a cutoff. So basically you're adding up. So, this is due to a single gamma 1, for example, the minimum gamma. This is, say, due to gamma 2, the maximum gamma. And, you have these monoenergetic electrons which give you this characteristic synchrotron emission. And if you have, and this is like a continuum, you have many of these, you have intermediate guys as well. This is almost like filled in. So when you add all this up together, what you get is something like this spectrum, right? So this is nu to the minus p minus 1 by 2, right? The same thing is true for inverse Compton. The spectral shape is somewhat different. It is steeper. It is, so inverse Compton is in this guy. It is somewhat steeper, but it also has a cutoff at the same frequency, sort of steeper cutoff at the same frequency, steeper cutoff at the same frequency. Right. So basically, the nature of this peaky curve is very similar. So in the meat of this nu, in the main range of these frequencies, the individual shape does not matter. What matters is their relative shift, right? So, for example, this is actually fundamentally related to that nu naught goes to nu naught, which is equal to EB by MC in case of synchrotron, goes to gamma squared EB by MC, right? Similarly, nu naught, if this is a photon, the inverse Compton case, it goes to gamma squared nu naught. So if you have, the seed photons, so this is actually nu1, this is after scattering, the scattered spectrum. So if you had a, you basically, you had a seed photons here, this gets scattered to this energy, right? So you have nu. Before scattering, it goes to this by gamma squared nu, right? It gets upshifted due to this gamma 1. And, the same photons get upshifted to this guy, gamma 2 squared nu. So it's the same sort of, it's a very similar process that the photons get upscattered in both cases to a frequency which is higher by gamma squared. So there's no wonder why you get a very similar looking spectrum as a function of frequency. Okay, so one very important and special case is that of V epsilon being the CMB. And V is defined such that, so CMB is a black body, cosmic microwave background, and so V epsilon is defined as this. So 8 pi epsilon squared by h cubed c cubed 1 by. Right. So this is just the Planck function, except that you have 4 pi. So it includes that 4 pi factor. So it includes, it basically is integrated over all solid angles. So this is just is equal to 4 pi times B epsilon. We can actually write it in terms of nu or in terms of epsilon. We are preferring to write it in terms of energy, which is h nu, energy of the photons. So this is the seed photons. These are the seed photons, which are upscattered by these relativistic electrons. Okay, is this clear?
So, sir,
yes.
I have a question.
Yes.
So how does one distinguish means synchrotron radiation from inverse Compton? I know that the ratio of power depend on B square, and
Yes.
I'm not able to get it
Okay.
clearly.
So generally speaking, for the inverse Compton, so basically the seed, for example, the CMB photons, they are they are nu naught. That is their nu is sort of the CMB peaks at few hundred gigahertz, right? Whereas this omega cyclotron, last time I did an estimate, this is like 10 hertz, right? So basically what this means is that if both of them get upscattered by gamma squared by the same uh, electrons, this will be much higher energy. So this will come in hard X-rays or gamma rays, whereas this will come in radio. So generally the thumb rule is, if you see power law spectrum in radio, it's very likely it's synchrotron, and the corresponding thing, if the same object you see in high energies in gamma rays, you will see inverse Compton. So I think I have an example. Good question, actually. Yeah, thanks for asking questions. So let me show if I have that example here. Okay, here, yeah, indeed I do have it. You see this Crab Nebula? You see Crab Nebula, the spectrum SED of Crab Nebula. This part is this minus P minus 1 by 2. This is the synchrotron. And the corresponding inverse Compton, you can see these inverse Compton models here, ICCMB and whatnot. These are, so corresponding to this, you have at much higher energies the same minus P minus 1 by 2 type spectrum, but the range is much smaller. Okay, do you see it? So low energy, it's synchrotron. At higher energy, there is a counterpart because of inverse Compton scattering. Okay, and it also depends on the optical depth of the medium. So in order for scattering to happen significantly, it's good to have a higher column of electrons, so that a lot more photons interact with electrons and get upscattered. So in the end, you have to just use the emissivity formula and see see where what is the exact number. But this is the thumb rule, that at low energies, it's synchrotron, and at high energy the same electrons give rise to inverse Compton. So last time I was actually talking about this cluster case where you have radio bubbles and you have this X-ray emitting inverse Compton plasma. Okay, so now let's move on to the next topic. Which is, so did it clarify it somewhat? Hello?
Yes, sir.
Okay.
Yeah.
Right. So here you make an assumption, and there are these thumb rules which we know of for typical values of magnetic field. For typical conditions, this is what you expect, right? And then you have to check whether it makes sense if you put in the model in detail. Okay. So now we are talking about this process of Comptonization. Right, Comptonization, or energy exchange between electrons and photons on repeated scattering. Now the question is when does the spectrum of seed photons get modified due to inverse Compton scattering, right? So this is the question. Under what conditions is inverse Compton scattering important enough to affect the spectrum of the observed photons? Okay, and for that, what we need is something called the Compton-y parameter. So let me define the Compton-y parameter. What is Compton-y parameter? So basically, Compton-y parameter is a quantitative way to answer this question. When is it that we want to, when is it that the spectrum of the photons gets modified due to scattering? Okay, and it actually is composed of two parts. One is this, which is this is fractional change in photon energy due to scattering, and times mean number of scatterings, right? So basically, suppose you have log plot. So you have like a black body spectrum, and there are electrons here, and they're they're isotropic electrons, and they are interacting with this photon field. The question is, when does the observed spectrum get significantly changed due to scattering, right? And the answer is given by this Compton-y parameter. If y is greater than an order greater than 1, then SED changes. SED changes significantly due to inverse Compton scattering. Okay, so mean number of scattering. So if you have many interactions between photons and electrons, then of course we know that photons can get a lot of energy from electrons, right? So both are important, number of scattering, and the amount of energy exchange in a single encounter, in a single event. In a single event, and how many events do we have? Okay. So let's see. Right. Okay. So how? So we have actually split it into two simple parts. So where does Comptonize? So this is called Comptonization. So when y is greater than or equal to 1, we say that Comptonization has happened. So what are we, when does, you recall, right? We talked about how is black body spectrum established, right? If we did this, how is the black body spectrum established, right? When photons and electrons collide frequently, right? So basically, or when optical depth of absorption is greater than or equal to unity, right? Now, it's a similar thing here, except that we are talking about scattering, not absorption. right? So scattering preserves number of photons, whereas in a black body, absorption emission, number of photons adjusts to B nu, corresponding to B nu T. Right here, the number of photons is conserved. So there is a fundamental difference. So even when tau scattering is much bigger than 1, you do not, your S nu is not equal to B nu, because this is not thermal process, because thermal process involves emission and absorption. So what happens in this case when tau Sc is much bigger than 1, that is, almost all the photons undergo Compton scattering, but no emission and no absorption. That is, the number of photons is conserved, rather than, so basically what happens is, so the spectrum goes to Bose, Einstein spectrum rather than Planck. So Planck spectrum is what? So this is one, right? So right. So this is epsilon squared. So just a sec. Let me write it in terms of nu. So this is twice h nu cube by c squared 1 by e to the h nu by kt minus 1. So this is the Planck spectrum. Bose-Einstein spectrum sort of differs from it. It sort of is, it has a similar form, but it has h nu minus nu naught by kt. So it has this chemical potential like term, which corresponds to the fact that number of particles is conserved. So this is Bose-Einstein. It is still like bosons, but it is not Planck spectrum. So when tau nu scattering is much greater than 1, rather than S nu relaxing to B nu T, it relaxes to this SED, which is a Bose-Einstein spectrum with a finite chemical potential. Okay, so I'm actually not going to talk about this in detail, but you can look this up in this book by Longueur. He talks about Comptonization a little bit. So let me go back to this condition, Compton-y condition, of when does spectrum get modified significantly because of inverse Compton scattering. Okay, so let's calculate a few things. So let's see. So let's consider this first. Consider this case of thermal non-relativistic electrons. So thermal non-relativistic electrons means that the electrons have a Maxwell-Boltzmann distribution, and their KT, sort of KT is much less than mc squared, right? So this is non-relativistic. Let's see. So in the electron rest frame, we have delta epsilon prime by epsilon, right? So the change in energy relative to the energy itself is minus epsilon prime by mc squared 1 minus cos theta. So if you recall, right? In the rest frame, we had this expression, epsilon prime is equal to epsilon by 1 plus. So this was 1 after scattering in the rest frame, 1 plus epsilon prime before scattering by mc squared 1 minus cos theta. Right, so where theta is the angle between incident and scattered photon in electron rest frame. Right, so this is the standard. This is the first thing that we did. So this is about epsilon prime 1 minus epsilon prime by mc squared 1 minus cos theta. If we are if the epsilon prime by mc squared is much less than 1, we are in the Thomson, almost the Thomson limit. Right, so this is what we get. This is just that, right? Delta epsilon prime, which is epsilon 1 prime minus epsilon prime divided by epsilon prime, is just epsilon prime by mc square 1 minus cos theta, and we assume isotropic distribution of electrons, so this gives you minus epsilon prime by mc squared. So this is the average energy loss in single scattering in electron rest frame. This is an average energy loss of photon in single scattering in the electron rest frame. Okay. Now let's assume, we have assumed that epsilon by mc squared and kt by mc squared both are much less than 1. So, right, so we can actually motivate. So we can actually motivate this expression. So let me first write this down. 2 minus epsilon by mc squared plus alpha kt by mc squared. So, you know, this is relative change in photon energy in lab frame. Okay, so in the electron rest frame, electron always loses energy, but if you in the lab frame, if the photons can gain energy if electrons are sufficiently hot, right? That is, if kT is much bigger than epsilon, right? So this is the photon energy in the lab frame. This is electron energy in the lab frame. If the typical energy of the electron is much larger than the photon energy, then the electrons should lose energy and the photon should gain energy. So basically this is what we have. So this is loss from this kind of a term, right? And this is gain due to inverse Compton scattering by energetic electrons. Now the question is, what is the value of this alpha? Alpha is something which is order unity, because you have to, right? You have to get a negative answer when kT is small and a positive answer, that is your photons gain energy when kT is big compared to epsilon. Now let's consider these are thermal non-relativistic electrons. So your Ne is equal to K E squared e to the minus E by KT, right? This is Maxwell-Boltzmann. Now let's look at delta epsilon. So is equal to minus epsilon squared by mc squared. I'm just multiplying this equation by epsilon plus alpha kt by mc squared times epsilon. And what I'm saying is that now let's talk about equilibrium. That is, so we want to actually determine this, this alpha, right? But what I'm saying is I'm actually going to determine alpha, but I am assuming that, like, let's assume thermal equilibrium, right? Between electrons and photons. So if there is thermal equilibrium, then delta epsilon is equal to 0. Right? So there is no change in the energy of photons once they are in equilibrium with electrons. So if we just do that, so this is like a statistical average, right? So what do we get? So this is equal to minus epsilon squared by mc squared plus alpha kt by mc squared times epsilon, right? So what is epsilon? Epsilon is equal to so basically n epsilon d epsilon divided by n epsilon d epsilon. Similarly, epsilon squared is equal to epsilon squared, n epsilon d epsilon divided by n epsilon d epsilon. And if we plug this in, we have epsilon cube e to the minus e by kt. So this we can easily calculate for this distribution function, Maxwell-Boltzmann distribution function. What do we get? We get 3 kt. And what do we get for this? We get 12 kt squared. Okay. So what do we have? We have, so this is equal to minus 12 kt squared by mc squared plus alpha kt by mc squared times 3 kt is equal to 0. So this, this determines alpha for us. This tells us alpha is equal to 4, right? So basically we have said that we have to determine this alpha, but we have actually applied the same equation and said that what if we approach equilibrium? In equilibrium, there should be no exchange of energy between electrons and photons. If there were an exchange of energy, that means the system is not in equilibrium. So this is like a clever way of obtaining this alpha. There are other ways as well, but in this way, it's quite simple. It's sort of like, we made this assertion that S nu will become B nu, right? For thermal emission processes. It's an argument similar to this because we apply S nu equal to B nu even when the medium is not optically thick, but we say that S nu remains the same whether it's optically thick or thin. So in the same way, this value of alpha, which is applicable even when the system is not in equilibrium, should be the same as when you evaluate assuming equilibrium. The same thing is true. This type of argument appears again and again in statistical mechanics. When we dealt with the Planck radiation, right? We introduced these Einstein's coefficients, and we identify this spontaneous emission and absorption and stimulated emission as fundamental processes, and we apply equilibrium, and then we obtain these Einstein's relations between A's and B's. Similar argument. This is a similar argument, very powerful argument. Okay. So what do we have? We have delta epsilon non-relativistic is equal to epsilon by mc squared 4 kt. So we obtain this alpha factor 4, and that's what minus epsilon. So this quantifies how much should the energy exchange be for this non-relativistic electron gas. So recall, the whole program that we are following right now is to actually try to calculate this Compton-y, and it has two components. One is this amount of energy exchange per collision, and the second is number of collisions. Right. So this is related to the first part. So what if for relativistic electrons, if instead of non-relativistic, if we have relativistic electrons, what happens in that case? So if you have relativistic electrons, that means kT is much bigger than mc squared, but we are actually assuming that epsilon is less than mc squared by gamma, because we are assuming in the Thomson limit in electron rest frame. So what happens in this case? So basically, in this case your electrons are much hotter. In fact, they are relativistically hotter than photons. So you can actually neglect this one. You can neglect this one because this is much bigger than that. So you have delta epsilon relativistic is like 4/3 gamma squared epsilon, right? So we neglect the possibility of electrons gaining energy from photons. That is actually negligible. This we actually obtained from the power formula as well, this 4/3 gamma squared factor. Okay, so how do we relate gamma squared to temperature? How do we relate gamma squared to temperature? Actually, let me not circle this. So we know that gamma squared is equal to E by mc squared. Again, even if you're relativistic, the Maxwell-Boltzmann distribution, again is the same, this one. So, right, and what we do is we actually just calculate E squared with that, and that gives us, we have actually already done this, right? E squared Ne dE is what we need here. So this will give us 12 kT by mc squared, the whole square. So delta epsilon relativistic is about, so 4/3 times 12 is 16 epsilon kT by mc squared, the whole square. So this is the relativistic expression. Recall, in this case, we don't consider this second term, this term. We don't because we are already assuming that photon energy is much smaller than the particle energy. Okay, so now what? So this is about, this is delta epsilon by epsilon that we were after, right? So if you recall, the program that we are following is we want this one, and we have calculated this for relativistic and non-relativistic thermal distribution, and now we are after this mean number of scatterings. What about mean number of scatterings? What about this? Right, so let me actually write down first. So mean number of scattering, number of scatterings is equal to max of tau es, comma, tau es squared. So tau es is electron scattering optical depth, right? So which is nothing but the size of the system divided by the mean free path. And can someone explain to me why we have tau and why do we have this expression max of tau and tau squared? We have actually encountered something like this before. So let me actually draw. Right, so when you are in the optically thin case, your mostly photons will travel in straight line, and rarely one of them just gets scattered. Right? This is thin case. What about the optically thick case? In this case, you have photons going around and eventually escaping. So in this case, what is the number of scatterings? Right, so e to the minus tau. Yes. Yes, please.
Yes, sir, I was saying that it was due to random walk.
Number of photons scattered by number of photons. Right, so this is what you have. And so this in this right, so this is equal to 1 minus e to the minus tau. Just a sec. So number of photons scattered divided by total number of photons is equal to 1 minus e to the minus tau nu. So when tau nu is much bigger than 1, all of the photons are scattered. When tau nu is small, this becomes 1 minus tau nu. So this sort of goes like tau nu and 1. When tau nu is much less than 1, this is tau nu greater than 1. So so the number of scatterings in this case is just tau nu, which is L by mean free path. So when tau is less than 1, what is maximum of tau square and tau? When tau is less than 1, it picks out 0.1 squared or 0.1, which is bigger. It picks out tau es, right? Because 0.1 is bigger than 0.1 squared. So the number of scatterings is tau es, which is the ratio of the size of the system and the mean free path. In this case, right, so we have this system size L. In this case, you have a random walk, right? And L is equal to, or L squared is equal to number of scatterings times the mean free path. This is just a random walk argument, right? That the L by mean free path, the displacement is proportional to square root of n rather than n. N is like ballistic. So in this case, the number of scattering is equal to L by mean free path squared, which is equal to tau squared. So when tau is much bigger than 1, your n scattering is tau squared. When tau is much less than 1, the number of scatterings is tau, right? So this expression is very, very common whenever we are sort of trying to write an expression which is valid for optically thick and thin regime. So this is optically thick, which is this number of scattering is tau squared. This is for thin. So number of scatterings is just the ratio of the system size and the mean free path. So so this is the origin for this. So what is Compton-y then? Putting it all together, y non-relativistic is equal to 4 kT by mc squared, maximum of tau es squared. Now here I'm actually ignoring or not ignoring that. I am assuming that kT is much bigger than epsilon. Otherwise, I should have taken this factor also. And y relativistic is 16 kT mc squared max tau es tau es squared. So this is evaluating this provides us the answer to the question, when is SED modified by inverse Compton scattering? And the answer to that question that we asked at the beginning is when y is greater than or equal to 1. Okay, so this is the answer. So let's actually do one application of this, for example. Okay, so let's again, galaxy clusters are the prime example for inverse Compton scattering. So you have a galaxy cluster. Average density you can take like 10 to the minus 3 particles per centimeter cube. You can take the size, the system size, to be 1 megaparsec or 2 megaparsec. Okay, so let's first calculate tau es. This is nothing but the size, which is 2 megaparsec times n sigma. All right, so what is tau? Tau is equal to integral n sigma dl, right? That's what I'm using. So number density is 10 to the minus 3. Sigma, can someone tell me Thomson scattering cross section?
10 to the power minus 16, I think.
No, your orders of magnitude off. So this is in CGS units. So megaparsec is 3 times 10 to the 24. So what is tau es? Is equal to, so this is 6 minus, it's quite small, right? Let's sort of make 6 10, because we're really doing order of magnitude. So this is 10 25 minus 25, so 6 times 10 to the minus 3. So this is actually much less than 1, right? So number of scatterings is equal to tau es, which is, so let's say, what was this? 6 are 36 times 10 to the minus 4. So this is 4 times 10 to the minus 3. So 0.004. And let me tell you the other things. KT, so the temperature of galaxy clusters is 10 to the 8 Kelvin. So what is KT by mc squared? Can someone tell me? So mc squared for electrons is 0.5 MeV, right? So what is that in Kelvin? 0.5 times 10 to the 6 times 10 to the 4. So this is like 5 times 10 to the 9 Kelvin. So this becomes 1 by 50. So you see Compton-y. So, and 10 to the 8 Kelvin, is it relativistic or non-relativistic? Someone?
I think that it's non-relativistic.
Yes, because temperature of order 5 times 10 to the 9 is when gamma is order 1. So this is non-relativistic. Even though it is very hot, electrons do not have a temperature which is like their rest mass energy in this case. So what do we have? So what is Y? So we should actually use this formula. And again, you know, F, so we are considering CMB. What is the energy of CMB photons? So it's 3 Kelvin, right? CMB temperature is 3 Kelvin. So it's actually much less than KT, right? Of these electrons, which is 10 to the 8 Kelvin. So we can actually indeed ignore this minus epsilon that was hanging there, right? This one, we can ignore this. So what is the Compton Y for galaxy clusters is 1 by 50 times 0.000. So 1 by 50 times 0.004, which is actually much less than 1. So what it means is that the CMB spectrum that we are looking at behind a galaxy cluster, so this is the CMB spectrum, the cosmic microwave background. Oops, sorry, not a good drawing. Ugh. So again, long plot. So this is nu squared, the Rayleigh Jeans part, and e to the minus h nu by kt. This is the Wayne tail. So this is the CMB spectrum. Now, if you're looking towards the galaxy cluster, how would the CMB spectrum look like? It would almost look like the same. It would almost be the same because Compton Y is much less than 1. Only a small fraction of photons get scattered, and that too, whenever the photon gets scattered, they lose, you know, the change in energy is small because KT is still much less than mc squared. You get it? So,
No.
although this is small, yes. Hello.
We have tau less than 1.
Yeah, oops, sorry. We have tau less than 1. Yes.
And so then what, sir? I'm not able to get it. Maybe some network issue.
What are you not able to get? Can you please ask specifically? Why is tau less than 1?
Because n sigma, we have calculated n sigma d.
Yeah. We have actually calculated tau, and we have assumed the Thomson scattering cross section. That's a good assumption, right? If you remember, there is something called Klein-Nishina suppression, but we are talking about, you know, that happens only when epsilon is much greater than mc squared, you know, or energy is much greater than mc squared. So we are not in that regime. So we just use Thomson scattering, and you know, you just calculate n sigma dl. We get a optical depth which is 0.004. So our Compton Y, which is the product of delta epsilon by epsilon and tau, for tau less than 1, this is tau, and if it was optically thick, then we should have used tau squared. Right, so our Y is much less than 1. That means the observed spectrum is not modified significantly, right? This is what it means. Do you get it?
This for temperature means my CMB or 10 to the power 8 means this is what
This temperature is the electron temperature. This temperature is the electron particle temperature. When we are talking about CMB, we are really dealing with epsilon. That's the energy, right? So I'm again using T. I mean, this is really TCMB, which sort of is like a typical energy of a photon, of the CMB photon. This is really epsilon, right? This gives a sense of epsilon. T is everywhere here. T is the electron temperature, not the CMB temperature, not the photon temperature. The photons I'm characterizing mostly here by epsilon. Okay, so this is what it means, that Comptonization is not that important for galaxy clusters. But is comptonization important anywhere else? Yes, answer is yes, in X-ray binaries. So X-ray binaries. So X-ray binaries are these accretion disks, accretion flows around black holes. And what they have is they have a black hole or a neutron star, they have an accretion disk. But in addition to this, they also have something called a corona. This is a corona. So corona has hot, KT of order mc squared, hot electrons, and they can, this can actually be pretty dense and long. So your tau can actually be greater than 1, and the photons can actually, rather than free streaming, they can get Comptonized and then come out. Okay. So for some of the X-ray binary, to explain some of the X-ray binary spectrum, you need to invoke Comptonization, right? And Comptonization means that your Y parameter is greater than 1. Okay, so let me now show you some examples. Okay, so this is that book. So this is that book that I was mentioning to you about, this by Longair. So let me go over some figures of this book, just to explain qualitatively what I mean. Okay, so yeah, so here is intensity as a function of frequency, right? So, and this is that chemical potential that I was talking about, mu, right? For Planck distribution, mu is 0. You have Planck distribution, so this is I nu is nu squared. But when you have scattering and no emission and absorption, then your spectrum corresponds to a finite chemical potential, and it's different from Planck distribution. It is a Bose-Einstein distribution with a finite value of mu. So you see how they differ. And when the medium is optically thick, but only with Compton scattering, you do not reach a black body spectrum. You reach something called a Comptonized spectrum, which is the Bose-Einstein spectrum with a finite value of mu. So this is illustrated in this graph. So you can ask me questions if you have any. I'm just sort of talking qualitatively now. Okay, so this is this book. And then what else? Okay, so here is an example of when Comptonization happens, right? So this is intensity as a function of energy of the photons, and basically, so the electron has an energy of 25 keV, and the seed photons are right. So this is from Monte Carlo simulations. So these histograms are from Monte Carlo simulations, and this is from analytic theory. So what happens is, so there are these taus, tau equals 3, tau equals 4, 5, 6, 7, and so on. So when tau becomes bigger and bigger, that means your Compton Y parameter is becoming larger than 1. So this is a Comptonized spectrum. So the seed photon spectrum has been totally changed because your Compton Y parameter is much bigger than 1. In all these cases, the seed photon spectrum is the same. So the larger the Compton Y parameter is, larger the deviation of the scattered photons is from the incident or the unscattered photons. So you can see optical depth becoming larger and larger, it becomes shallower, and it starts to develop this wean tail, right? This one starts looking like a black body, but this is not a black body, but it is a Maxwell-Boltzmann, it is a Bose-Einstein distribution, right, which is obtained for large optical depths, but in absence of absorption and emission. What else? For example, so this is the example that I talked about. So you have this CMB spectrum in this black, which is not scattered. This is the CMB spectrum. But if you're looking towards galaxy clusters, Compton-y parameter is small, right? It was like 10 to the minus 4 or few times 10 to the minus 4. But you also should know that the CMB observations are extremely accurate. So even tiny variation from the black body are detectable. So even though the Compton-y parameter is tiny, we can actually see this effect of Comptonization on some photons, and this modifies this black body spectrum to something like this. So the dashed line is the spectrum after it passes through a galaxy cluster. You see the total number of photons has to be conserved, right? Because it's scattering. But the mean energy of the photons has been increased to a slightly larger value. So this is the solid black line is the CMB spectrum, and 10 to the minus 4 or 10 to the minus 3 of these photons get a positive kick in energy, which corresponds to right. So which corresponds to wavelength becoming smaller. So wavelength decreases along the right here. So this is your scattered spectrum. But remember, this is highly exaggerated. I told that the spectrum does not get modified much if your y is much less than 1, which is the case in this case. But here it has been highly exaggerated. Let me this book goes through a lot of this in great detail. So here is an example of measured distortion of the CMB from some galaxy cluster. No, this is Monte Carlo simulation, but these are actually observations from galaxy clusters. So you see, at low frequencies you have a suppression of flux, and at high frequency you have excess of flux. So if you go back here, you see at low frequencies your observed spectrum should be slightly lower, and at high frequency your observed spectrum should be higher, and it should be the same at this frequency, which I think is 220 gigahertz. So if you go to these real systems, you see this is 220 gigahertz. You have a null. Here you have a decrement, and here you have an excess. So this is called Sunyaev-Zeldovich effect, SZ effect. Okay, and it's actually very, very important in detecting and finding new galaxy clusters at high redshifts. And you see this signal is actually tiny. This delta I, what are the units? Just a sec. The observed SZ spectrum associated with hot gas in clusters of galaxies. Solid line is the best fit model. So this is change in intensity, and the magnitude of this change is actually 10 to the minus 3, 10 to the minus 4, which has to be true because we calculated the Compton-y to be 10 to the minus 3, 10 to the minus 4. So it has not been divided by I. It has been given in this. The change is given in megajansky per steradian. But the idea is this, that this is the application of inverse Compton scattering. Okay, so what I'll do now is I think I'm mostly done with Compton scattering and inverse Compton scattering. Okay, so I encourage you guys to read up the material that we have covered. And appreciate this close analogy between synchrotron and inverse Compton scattering. Okay, so from next class onward, we will talk about propagation of electromagnetic radiation from a plasma and effects associated with this. Okay, so are there any questions? Let me, oops. let me stop recording.